So yesterday in your video notes, you did the centroid and the orthocenter. And so we're going to start off on the triangle points of concurrency notes continued. That was the second set of notes. So there's basically two sets of notes. The first set of notes are what are the facts. This is what are the facts about the triangle point of concurrency, and then the second set of notes is going to be kind of the mathy examples. So, triangle points of concurrency continued. Okay, you guys ready? Okay. So it says, find the coordinates of the centroid of the triangle. There was actually one similar to this on the video notes last night. So any idea? Let me remind you. Here it is. Here it is. So what do we do to find the centroid? What do we do to find the centroid if we have a picture? Yes. Uh-huh. Uh-huh. The x value. Mm-hmm. So we're basically finding like the average, right? Okay. Court, you want to put the stapler away and maybe get out a sheet of paper? Marvelous. All right, so we have G, H, and I. We're going to go ahead and write down what all those points are. So G is 2, -4. H is -1, -7. I is -4, -7. So what we're going to do is we're going to take all of our x coordinates and we're going to add them together. So we've got 2 plus -1 plus -4, and then we're going to divide them by 3. So we're going to find the average of all the x coordinates. The average of all the x coordinates. And what does that give us? -1. So we got 2 minus 1 is 1, 1 minus 4 is -3. -3 divided by 3 is -1. And then y, we're going to take the y's, -4 plus -7 plus -7 divided by 3. So we got -11 minus 7, -18 divided by 3, -6. So the centroid is an x-coordinate of -1 and a y-coordinate of -6. X-coordinate of -1, y-coordinate of -6, so right there. One of the things that we know about the centroid, it's the medians. It's where the medians are concurrent. This is one of the triangle centers. I think this is one of the ones that's inside. Yep. This is inside the triangle, so that's good. Kind of looks right. Okay. All right, you guys feel comfortable on that example? Okay. All right, let's do example 2. So the things that come into play in example 2 is that that the median, it connects to the vertex, and so the median connects and it bisects the opposite side. So that means that wherever the median cuts into the opposite side, we know that these two pieces are going to be the same. That's how the medians work. So that's one part. And then the other part of the problem is that we have that 2-to-1 ratio. Okay? So those are the two things we have to keep in mind when we look at these problems. So the first thing I'm going to do is I'm going to say, okay, if this is 8, then this is 8. That's the first thing I'm going to do. Okay? Because that's how medians work. AG is 10, so if this is 10, here's the 2-to-1 ratio. If that's 10, this is 5. There's the 2-to-1 ratio. And then it looks like I moved the picture over too much. CD was supposed to be 18. That didn't print in the notes. CD was supposed to be 18. So if the entire length of something is given, and you have to solve for that 2-to-1 ratio, the easiest thing to do is to set up the 2-to-1 ratio yourself. So I'm going to label that this is x, and I'm going to label that as 2x. Everyone see how I gave that 2-to-1 ratio when I labeled my variables, x to 2x. There's my 2-to-1 ratio. And then I can just write a little equation, x plus 2x equals 18. So I didn't make up the 18 off the top of my head. The 18 was supposed to be there, and I think I just moved the picture over too much when I made the notes last night. And so the picture covered up the number. That was my bad. All right, so we've got 3x equals 18. And then if we divide by 3, what do we get? X equals 6, okay? So that would mean I'm going to go back, because my picture's small, I'm just going to go back and erase that. Maybe not. I'll put it underneath. So x equals 6, and then 2x equals 12. Okay, so then we got 6 and 12. Okay, I'm guessing we probably have everything that we need. I'm thinking, probably. So BD, okay, BD is 8. AB is 16. 8 plus 8 is 16. EG is 5. EG is 5. AE is 15. CG is 12. DG is 6. Okay. How do you guys feel about the example problems? Feel pretty good? Okay. So pretty common for them to use this median, that it bisects that opposite side, so it cuts that opposite side in half. That's one thing to keep in mind. And then also keeping that 2-to-1 ratio in mind. So if we look at the problems, what I did is I kind of gave you sections of problems. So if you look, the problems that go with this section are the first page of the assignment. So there are 4 problems that have to do with the centroid. With the orthocenter, there's no question. We just memorize facts about it, basically. There are questions that I've seen online, but they are in a more advanced math class. So, Sam, thank you for the smile. I saw the crinkle eyes, so I knew that you were appreciating my humor underneath your mask. I do appreciate that. Thank you. Thank you for the support. So, let's go ahead and get started on the assignment. Our goal right now is to do problems 1 through 4, and then we will continue with our notes. Okay? So, we'll just see how far we get 1 through 4, and then continue with our notes. I will be working on an answer key and printing a copy for you. Okay? Well, I mean, can we continue? So our next triangle center of concurrency. I don't know why I said that in a fancy voice. Concurrency is the circumcenter. Let's get to our circumcenter notes. Did everyone make note of this? Did I make note of this in the video? Right there, this one, this example for the orthocenter? Okay, because that's a math fact that they like to throw out there. And we know there's not very many orthocenter questions, so that's one that's going to come up. Okay. All right, the circumcenter. The circumcenter. Hold on, let me get my life straight. I have way too many papers up here. Okay. The circumcenter is where the perpendicular bisectors are concurrent. Where the perpendicular bisectors are concurrent. Perpendicular bisectors. So perpendicular bisectors, I know this is going to be such a strange definition for a perpendicular bisector, but they are perpendicular to the side. Oh, not PR, PER. They are perpendicular to the side. I ate lunch over here and my desk is sticky. Okay. Perpendicular to the side and bisect the side. So the difference here is they do not go through the vertex. They could go through the vertex, but typically do not. So perpendicular bisectors. Perpendicular bisectors. Perpendicular to the side, and they bisect the side. The thing that is interesting about them is that the circumcenter is also the center of the circle that can be circumscribed. About the circle. About the triangle. So, and here's how it works. You can see it in the examples. So if you were to take the center, the circumcenter, and then draw a line from the circumcenter to each vertex and call that a radius. So from the center to the vertex, that's a radius. From the center to the vertex, that's a radius. From the center to the vertex, that's a radius. Then you could create a circle from that, and that would be the circumscribed circle about the triangle. And this is unique. This is a fact about this problem. And this is a pretty interesting fact. I would maybe highlight that. This is something that they like to use a lot. Okay, and they will draw that in triangles. They will take a line and draw the line from the center to the vertex. They'll have already drawn the perpendicular bisectors, and then they'll draw extra lines in the problem. They'll make them dotted lines, and they'll expect you to know that each of those lines from the center to the vertex, that each of those lines are the same measurement, or a radius of that circumscribed circle, okay? So this is an interesting fact, and it's one that is a little bit hard to recognize, so it's one that I'm going to hammer in there in the math problems that we do, okay? Because it's a weird one. I think this is kind of the more interesting example right here. So again, we have, this one is kind of weird that the circumcenter happens to be outside the triangle. You guys see it? The circumcenter is like way outside the triangle. And then from the circumcenter to this vertex, the circumcenter to this vertex, the circumcenter to this vertex is a radius of that circle, which is just super interesting to me. So the vertices, what I was just saying, are equidistant from the circumcenter, and in parentheses I'm going to write that they're a radius of that circumscribed circle. Actually, I'm going to put that in radius of the circumscribed circle. All right. The circumcenter does not have to be inside the triangle. Circumcenter does not have to be inside the triangle. Okay. If you have a right triangle, the circumcenter ends up being right on the middle. It's the middle of the hypotenuse. Do you guys see it? So in a right triangle, it's in the middle of the hypotenuse. Kind of odd. It's an interesting math fact for it. I used to not point this out. I used to be like, oh, it's just a strange thing. It's kind of interesting. And then I started to notice that these were sometimes multiple choice questions. Like, why, EOC people? Why do you have to cling onto something so obscure and make it an EOC question? That is annoying. But there it is. So there's the circumcenter right there for the right triangle. All right, this is not an EOC question. I just thought it was interesting. Okay, random math things are interesting to me sometimes. So Leonard Euler, that's right, I did not pronounce this wrong. It is literally pronounced Euler. I'm going to write this in quotes. Euler is how you pronounce it. The same guy who gets his own number. He noticed, because math people, for whatever reason, they have like their little paws and everything. So they have all these unrelated things. They're like brilliant all across the board. They notice all these things. He noticed a relationship between the three classical triangle centers. They are collinear. Collinear means they're in a straight line. The centroid is always in the middle of the other two. The distance between the centroid and the orthocenter is always twice as much as the centroid and the circumcenter. The line that these three centers of triangles lie on has been dubbed the Euler Line. I'm telling you now so that if you ever go on Jeopardy, and this is the Jeopardy question that wins you $1 million, you can thank your high school math teacher. Okay, this is the Euler Line. 2-to-1 ratio, circumcenter, centroid, orthocenter, centroid's in the middle. Okay, so if you guys ever win Jeopardy because of this math question, you can thank me. Log it in your brains. Or are you guys all logging it? So that if you're on Jeopardy and you win, you know who to thank. Miss Rice, Eno River Academy, thank you. Shout out. Hashtag appreciate you. Okay. All right. So there's the circumcenter. Okay, let's move on to the circumcenter questions. All right, here we go. So anytime I see a problem where they tell me that was a whole laptop that just went crash, bang, boom. All right. So anytime they give a problem and they say something about perpendicular bisectors or they say circumcenter, anytime they do that, now remember, circumcenter is circumscribed. Get it? Circumcenter is circumscribed. No? You guys don't want me saying that? Okay, that's fine. So anytime I see that, I'm going to go, ooh, I got a circle. Does that not look like it's kind of a lopsided circle? Nobody? No? You guys are not engaged in my lesson right now. Where are you engaged over there? Well, that looks more circular. That's pretty good. Okay. So anytime I see that, I just train myself to draw the circle. And the reason I do that, remember about the radius thing. Helps me remember. Otherwise, I've noticed that I personally forget that. And this kind of just helps me. Okay, so here's my center. So we've got from the center to the edge, is 25. You guys see that? My radius is 25. And that radius is going to stay the same. This is going to bug me that this is not good. Miss Rice, it's not good. Hold on, I'm going to fix my circle. I can make it better. How did your guys' circles turn out? Are they good? That makes me feel a little bit better. We can all be in this together. Well, that's better, maybe. Ooh, look at that. You guys, look at that. That kind of worked out. Okay, is that kind of circuit? That's pretty good. That's very nice. If I do say so. Okay, so from the center to the edge is 25. That's a radius. So then from the center to the edge, ooh, that's 25. That's another radius. Ooh. And then from the center to the edge, that's 25. That's another radius. Oh, thank you, thank you. Okay, and then we've got a perpendicular bisector and a perpendicular bisector. And then, ooh, a wee little perpendicular bisector. Okay, so since these are perpendicular bisectors, they bisect, so it's 20, 20, and 15, 15, and 24, 24. See how we were able to use all that information? Are there any questions on that one? Did it make sense how we could fill in all those numbers real easy like that? Yeah. Okay, so AG is what? 25. BD is 20. CF is 24. AB is 40. CE is 15. AC is 48. Measure of angle ADG is 90 degrees. Okay, BG is 2x minus 15, so we're going to say 25 equals 2x minus 15. And then we can add that 15 over. And divide by 2. And x equals 20. That was fun. That was nice. How do you guys feel? Terrible? Well, come on. Circumcenter? Okay, this will make you feel better. When I was teaching this years ago, Wade, I saw that. Don't put your hands up like you're innocent. Jack, why are you playing pool? For shame. When I was teaching this exact lesson, are you listening? I was teaching this exact lesson, and instead of saying circumscribed, I said circumcised. The circumcised triangle. Like every time? No, just once. But triangles do not get circumcised. That is not a thing that triangles do. And then my base reaction was, oh, just kidding. That's a thing that happens in the Bible, not in math class. That Sunday school goes strong, you guys. That Sunday school goes strong. All right, let's move on to the next problem, shall we? Example 4. Who's ready for example 4? So, I got my perpendicular bisectors. That means I'm drawing my circle. No, we've already been here, Joseph. I said that pictures do not count for taking notes. Yeah, we've been here. No, but it was notes, Joseph. We've already been here. Taking pictures do not count as putting effort in. This is still the continued notes, just the second page. Okay, here's my circle. This was pretty good for, a kind of first try-ish. All right, here we go. Okay. Whew. I'm going to zoom in so Court can see, because I know that he's very engaged in this lesson. Yeah. It's triangle points of concurrency. All right. So if we were trying to solve for x first, let's say we were trying to solve for x first. The x is over here. What should I set it equal to? 24. Okay, so I'm going to say 8x plus 16 equals 24. So what we're saying here is that this AR is a radius just like the 24 is. So it's a radius of the circle, it's a radius of the circle. The circumscribed circle. There's some mistakes you don't make twice, folks. Yeah. All right, 8x equals 8. All right, what'd you guys get for x? X equals 1. Marvelous. All right. Now, if I wanted to solve for y, how would I solve for y? Use the 24 as the radius again, because 5y minus 6 happens to be another radius of the circle. So 5y minus 6 is another radius, so we're going to set it equal to 24 as well. Did everyone catch that? The radius again, so we're going to use the radius. All right. Plus 6. What'd you guys get for y? Marvelous. Okay. And then what do we do to solve for z? Okay, so now we're using the fact that it's a bisector, so this side is cut in half, so the two halves must be equal. So 18 equals 7z plus 4. And what do we get for z? 2. All right, go ahead and work on your practice assignment again. Or would you guys like to do in center? You want to do in center or you want to work on practice? Practice? Okay, let's work on practice. Whew. All right. The in center. The in center. The in center. No? Anybody? No? The in center. I'm just waiting for some quiet. I'm waiting. I'm still waiting. All right. The in center is where the angle bisectors are concurrent. Where the angle bisectors are concurrent. Okay. The in center is also the center of the circle that can be inscribed in the triangle. So if you can draw a circle inside a triangle where the circle touches all the sides, can you guys see that? The circle touches all the sides. That is a circle, or where the center of the circle is the in center. So if that is the case, then the sides of the triangle are equidistant from the center, and that means that the, oh my goodness, I can spell, radius has an A in there. The radius comes from the center to the side. And they will often, what they'll often do here that can sometimes mess students up is to tell you that they went straight from the center to the side, is they'll draw the 90-degree angle there to tell you that it's perpendicular, that they went straight from the center to the side, so that it's not at an angle, because that's how you maybe not, maybe I'm wrong about that. Maybe don't draw that in there. I'm trying to remember, and I was thinking that's what it was, but in these pictures, that's clearly not true. So don't write that. Ignore me for a second, and I'll, if I notice that that's true in other pictures, I'll bring it up again. But that might not be the case. All right, so the sides of the triangle are equidistant from the end center. There are two of these triangle centers that are always inside of the triangle, and then two of them that can be outside of the triangle. So we want to go through and we want to label which is which. So this one has to be inside because you've got that inscribed triangle. So we're going to say, just a little side note here, it has to be inside. Okay. And then if we look at our notes, you can see that these are the two that don't have to be inside because we can see samples of them where they are outside. So I'm just going to write a little note to myself for this one. Even though I can see it in a picture, I might not remember that. So I'm going to say can be outside the triangle. It's already written as a note for the orthocenter that the orthocenter doesn't have to be inside the triangle. And then for the centroid, it's an extension of this average idea, but if you're finding the average of three numbers to represent the centroid, then the number that you end up getting for the centroid is going to be inside. All right. It also makes sense too because the centroid is the center of gravity of the triangle, and so that would mean it has to be inside the triangle. So the centroid is another one that has to be inside the triangle. Okay. The reason I'm adding these to your notes is because this is a common multiple choice question, is which two are inside the triangle, which ones are outside the triangle. Say that again? Okay. This early? Are you guys doing something fun for us? I don't know. Oh, that's exciting. We have cheerleaders? Since when? Wait. But wait, for how long have we had cheerleaders? This year? But not previous years. Really? Where have I been? Okay. All right, let's do our in-center mathy examples. We need these. All right. So, here we go. Whenever they say in-center, I always draw the inscribed circle. This one's a little easier to draw. Inscribed. Inscribed. That's okay. There we go. All right, in the diagram below, oh, it's an isosceles triangle. Anyone remember what isosceles means? Yeah, two sides are the same, one side is not. Okay. AB and CB are congruent. All right. Hey guys, AB and CB are congruent. These two sides, they're congruent. Okay. Same. Okay. And angle bisectors AD. Okay, so AD is a bisector. That means that this is the same as this. BF is a bisector, so this is the same as this. And then this is the same as this, and we know that those are angle bisectors anyway because we're in the incenter section. So, but they told us in the problem is angle bisectors, which means we now officially know that this is the incenter. Okay, they intersect at X. The measure of angle BAC. BAC. So this whole thing is 50. So if this whole vertex is 50, what are the two angles? 25. Okay. Now, since this is an isosceles triangle, what does that tell you about angle C? It's going to be the same. So that means if angle A was 50, then angle C was also 50, and so these are also 25. Okay. Now, they didn't give us any information, but we know if they did that these three are the same because they're each a radius of the circle. So if they had needed something for this problem, then we could have solved it, but we didn't need to solve it because they didn't ask. Okay, so we're not worried about that. So I'm going to go ahead and just kind of lightly erase this. These are notes. I'm just going to, maybe I'll leave it in as a dotted line. This problem is strictly dealing with, I'm going to leave it in as a dotted line. This problem is strictly dealing with angle measurements, and so we didn't really need those sides. But, I don't know, interesting to remember that. Okay, so it says the measure of AXC. AXC. So the measure they want is this one right here. That is the measure we are trying to find. So how could we find the measure of AXC? Okay. So you're saying, well, that's assuming we don't know anything about this angle. It's probably 90, but we don't know that for sure. Because we're assuming that, but we don't know that for sure. But there is another way we could get it. We just have to think of a different triangle. I'm going to go with... We could do it a slightly different way, Vaughn. What do you think? Yeah. So if you, instead of thinking of it as two triangles, if you think of it as one triangle, so think of this whole thing as one triangle. Does that make sense? And so then you don't have to break it up at all. It doesn't matter what that inside angle is because you have a triangle. So if I do 180 minus 25 minus 25, now, Emma, you're probably right. It's probably 90. I'm just playing devil's advocate because we don't know for sure. So, and in math, we can't use anything unless we know. So if we do 180 minus 25, what do we get? 130. And so that means that this is a 130-degree angle. And so we're going to say the measure of angle AXC is 130 degrees. Boom. Done. Pow. All right. Example 6. Okay, so in example 6, they told us that T was the incenter. And since they told us it was the incenter, then we go, okay, since we know what an incenter is, then we get to go through and we get to just say okay, this angle is the same as this angle is the same as that angle, this angle is the same as this angle, and we get to go through. See, this is what I was referencing when I said I think that they do this sometimes. That if they're going to measure from here straight out to the side, they'll draw a 90-degree angle to tell you that they measured straight out to the side. But it's not, apparently it only is true that they all draw it that way on some triangles, but not all of them. Because some of those triangles in the notes packet definitely didn't look like that. So let's go ahead. We've got our inscribed triangle. Let's label what we can from that inscribed triangle. So we have a radius TW. The radius is 15. What's another radius? TS, TU. So we got 15, 15. Okay, so let's go ahead and answer our first couple questions. So they say, what's ST? That's 15. If TU equals 2x minus 1, find x. So TU is 15. If 15 equals 2x minus 1, find x. We can go ahead and solve that pretty easily. Don't you love these little equations they have us solve? It's like, thank you for making me solve that. I could have solved that a few years ago. All right, so we got that. Okay, then we've got PRT is 24. So PRT is just half. That's 24. So if that's 24, then this is 24, because it's an incenter. So they said if PRT is 24, then QRT is 24. Okay. The next one says RPQ. RPQ. So if RPQ is 62, so then they're 31, 31. Okay. So if RPQ is 62, then RPT is 31. Okay, so those notes are done, and we are ready to work on the rest of the assignment for the next 25 minutes. For the next 15 minutes, because we got another one of those pep rallies. Huh? Yeah, but this one's actually going to be more peppy. Yeah. Well, we have to do another one because the soccer team is continuing. That's why we're doing another one.